No.
Okay, so final talk of this session, given by Marylou, Gabrié from École Polytechnique. She'll be talking about opportunities and challenges in enhancing sampling with learned transport maps. Please, Michelle.
Yes, so thank you very much to the organizers for this great event. So I'm going to talk about a line of work that definitely combines stochasticity, maybe not stochastic calculus at this point, but stochasticity, optimization, and statistical mechanics, but somehow in a way that hasn't been yet explored, I would say, by this talk. So it's a line of work that I've been working on for maybe the past couple of years, with along the years a few people joining the discussions. And I will try to give you, let's say, an overview or mainly focus on the intuitions of why maybe we could use generative models from machine learning to accelerate sampling, and so to, if you want, mediate faster algorithms for high-dimensional inference. And that's precisely my starting point of motivation, is that there are many cases, and statistical mechanics is one of them, where we have a known distribution of interest, which we know maybe up to a normalization constant, and we want to infer some statistical properties from this distribution that needs oftentimes high-dimensional. And so, okay, so statistical mechanics is definitely a domain where this happens with our Boltzmann distributions on states of physical systems that could be denoted by the variable x. And it's also the case in Bayesian inference problem. And here, and we haven't heard so much about Bayesian inference inside state, but I'm sure it's familiar to most people in the audience, where you have a set of data, and the set of data, which I will describe, will induce a posterior distribution on the parameters of some model that could explain the data. That would be x, and you want to collect information about the statistics of such posterior distribution, because, for example, it gives you access to some uncertainty measure in your modeling of the problem. And here, the little example I give is this case of astrophysics, where there are observations of the star in the planet system. What you see in practice is the star that is going towards you and away from you periodically in your chain of sights, because of the rotation of the planet around the star. And you have few observations of this phenomenon, because observing is very costly. So you have a few dots of this radial velocity as a function of time. And you know the system is periodic, but if you have just those few little points, you can have multiple periodic signals that fix the data. And so you have a collection of models that give all these gray lines. I'm sorry, it doesn't show so well, that could explain the data. And so you want to have an idea that you have all these uncertainty in defining the parameters of your periodic model explaining this phenomenon. So, okay, so this happens oftentimes today. And of course, you know that the direct inference that would be actually trying to compute from the knowledge of the distribution some statistic of it is going to be exponential in the dimension. So you have, so this is not generally not an option. And so very commonly what we do is we resort to multi-variable methods in which we are going to approximate expectations with empirical averages. And of course, then we move the problem from computing an exact integral to obtaining samples from the target distribution. And something we've actually already been discussing in this workshop is that this sampling itself can be exponential. So we've had some talks about the exit times of basins being exponential, and some Arrhenius laws in invert the temperature with the difference of energy between the bottom of the basin and the exit point of the basin. Well, oftentimes in statistical mechanics, those energies, they are extensive. So they are linear in the dimension, and then this translates into an exponential in the dimension time of converging any multi-variable sampler that would be relying on those local random walks. And so this is why this is still very costly. So what I will try to tell you is how could we use deep generative models, or try, to speed up sampling, and this is really just the teaser. So before I enter into the detail, I wanted to make a little reminder of some generic Markov chain Monte Carlo algorithms that I would say are really, the all-purpose go-to algorithm that you can try if you have a new system you don't know anything about. And in particular, I'm assuming a lot of you have heard of this Metropolis Hastings sampler, where the idea is that if you have a target distribution from which you know the density that I represented by the side, then you can use a proposal distribution that I represented by rho p to iterate the following processes, where you, from a random initialization of a state of the system, you try to propose to jump to a value xt plus 1 from xt, and then you accept reject with the Metropolis acceptance criteria that will put into balance the target density where you are trying to jump from where you are coming from, but also what was the proposal, the probability that you propose such a jump and the reverse jump, in such a way that under relatively mild condition for, let's say, nice enough systems, you have a non-purpose algorithm that at long times will actually provide you with samples from row star. So that's a little recollection of the Metropolis Hastings. And if I'm being very down to earth and give you a very concrete example, I can think of this two-dimensional problem where you have this Muller-Brown potential, there's a term potential with metastatic states, and where I have high density that is in light color and dark density and low density that is in high density in light color, so that's the white, for example, and low density that is in dark color. And if I'm, for example, trying to use a Gaussian proposal in the Metropolis Hastings algorithm I was just recalling, I start from there. I will see that after 100 steps, I found the high density region. Very well. I can be a bit more sophisticated and actually go towards using gradient information, and that would be a Metropolis adjusted version of the Langevin dynamics we've talked a lot. So we just draw some Gaussian noise, but around the position that has been updated in the direction of decreasing energy. And then you could, repeat the procedure and move a bit faster towards the region of interest. But of course, again, the problem is that if I, instead of running 100 steps, I run 10,000 steps, I'm going to have issues with those energy barriers in between the metastable region. And of course, it's not because I would be using proposals with a larger variance. For example, in this Gaussian random walk example, if I was using the steps that were larger, I will not get anywhere and in any way faster in my algorithm, just because then the acceptance rate of the Metropolis Hastings is going to go down. And so each time I accept, I jump, but most of the time I don't accept and I don't jump. So we have, of course, this, in theory, very powerful algorithm, but in practice, very complicated. Metastable systems are very challenging for this type of algorithms. So of course, here I just represented this Metropolis Hastings because I will need it down the line, and I think it's also a good thing to have in mind for those types of problems. But there are full literature of more sophisticated methods of how to approach be it metastable or not metastable systems with sampling methods. And that's non-exhaustive list of the different directions you can go in. But what I would like to explore and tell you about today is a line of work that is going to use deep generative models to try to assist this sampling procedure. And I wanted to start by introducing those beasts. So and I will focus on a specific type of deep generative models that I call here based on transports. But so generally speaking, what I need you to know about models, in case you haven't encountered them before, is that many of them work in the following way. They have a latent distribution. This is my rho B, our base distribution. That is simple, that I know how to sample from, let's say a high-dimensional isotropic Gaussian. And I will learn a transformation that is a T index theta standing for the parameters. So that's when I transform the samples from the base distribution, then I get samples X, so that this T theta of Z. that are also from this implicitly defined distribution rho theta of X, if you want, and that are going to be able to reproduce a data set I chose in learning by transformation theta. And for example, you can nowadays do this like the following one, where you transform an image of a completely Gaussian random noise into an image of a dog after learning this transformation T theta on a data set of images of dogs. And precisely, you didn't learn how to transform one Gaussian noise into one image of dog. What you've learned is that each time you draw a new Gaussian sample, so you sample from this row BZ, you are generating a new image, a new sample that resembles the data you learned the transformation from. Okay, and one among these, well, maybe actually, I should say that in this category, you could think of generative adversarial networks, so GANs, if that rings a bell for some of you, or variational autoencoders. But nowadays, there are actually another line of networks that are even more used, I would say, and those are the networks that are based on invertible maps. So where you impose that your T theta is actually a diffeomorphism in such a way that you can even write down explicitly what is the rho theta of X just using the change of variable formula, provided that you've put yourself in the condition where you know how to compute the inverse of the transformation, and you know how to track the determinant of the Jacobian of the transformation or its inverse. And so here it can be done in different ways. I'm not going to enter into the detail, although if you're curious, I'm happy to tell a bit more. But I mean, such network could be normalized in flows. And then I could also be doing things a bit more related to the diffusion we've talked a lot about. If I were building store-based diffusion models, I mean, all of them enter into this box. But here, for the purpose of the talk, I just ask you to trust me that you are able to define transformation in this way, that are diffeomorphism. You know how to write both the direct map and the inverse map, and you know how to compute the determinant of the Jacobian. And okay, just if you are curious in a minute, how do you train such a transformation T theta in this framework? Actually, it's easy. You can just do maximum likelihood. So I say that I have a set of training samples. So think a set of images of dogs, and those are a set of xi that I assume to be IID. Now I can write what's the likelihood of my model that corresponds to a given rho theta to for these data sets. And so it's just going to be the product of the density at all the data points. And here, I mean, I can write an objective, a training objective, to maximize this likelihood to find the values of the parameters of the generative model. So far, so good. Yes?
That very last bit, I'm sure it's what people do, but isn't it really a negative thing to do in high dimensions? I mean, likelihood is just not a good measure in high dimensions. So the most likely Brownian motion is the zero Brownian motion.
Yes, so that's maybe a good question, but a good point. But here you should really think of it as indeed there is a regularization that is hidden underneath by the fact that we are modeling this distribution with neural networks. And actually you are trying to have something that interpolates the data, but you have a huge set of data points, and you are trying to learn about interpolation, density that is interpolating this data. And I think maximum likelihood there is very robust in practice. So okay, so we have these beasts. They are able to produce apparently highly complicated, highly structured type of realizations, but in very easy way. I mean, once the training is done, you can just sample a Gaussian and obtain a sample of a seemingly very complicated distribution. So it feels like there's really an opportunity in using them for sampling, I mean, systems we are interested in, be it the Bayesian posterior, or be it maybe the configurations of a molecule we want to model. So that's the question we are asking ourselves. Can we use those generative models for sampling? So I remind you a bit my notation and the overall goal. I have this rho theta of X. I know its expression, of course, up to this normalization constant Z, which I generally don't know. And I have this very expressive parameterized family of distribution, rho theta of X. Questions? Well, can I train actually? So here I'm using flow, sorry, because this baptiste theta is called a flow in some context. So can I train to have an approximation of rho star by rho theta? And this is my first question, and it's non-trivial, but for the following reason. That's in practice, as I was saying, where people do machine learning and generative modeling in machine learning, they have huge amounts of data, and they want to do density estimation. We are in the other way around. We have the measure up to a normalization constant, but we don't have data. Data would be samples from rho star, and samples from rho star are what we are after. So it's a slightly different setting from what people are doing in machine learning. So there is this question of how do we organize a training that would allow us to have a rho theta that is trying to approximate this rho star? First question. And then the second question I think we should worry about as good scientists is, okay, I mean, if I manage to learn this rho theta and to have a training objective that would take my rho theta towards my rho star, what use can I make of it in a controlled way, right? Because as I was telling you, actually this rho theta has a lot of deep neural networks in them. We have no guarantees whatsoever what this type of map can model as a rho theta, how the optimization will go. So we have no guarantees. So things will always be approximate, even if I manage to have, a way of going towards rho star. So how can we use an approximation in a controlled way and to obtain reliable samples? So those are the two big questions, and I will try to skim over the intuition of the answers and also go up to where we are now and seeing the limitations and how we are seeing, and ways of going beyond that. But maybe, so the answer of this first question of how to train is something that has been done in statistical mechanics already many times, and that's also in statistical, and statistics is called variational inference. So I don't know if the statistical physicists in the audience remember their mean field description of the fully connected Ising model in the Curie-Weiss model. What you do there is that you say, okay, I have an ansatz for the Gibbs measure that is a tractable ansatz of actually independent spins. And then when I do that, I can minimize the Gibbs free energy with this ansatz to predict to have an approximation of my target Boltzmann distribution. Well, this is exactly the same procedure as saying that what you're going to try to do is learn parameter theta such that the pullback divergence between your model rho theta and your target rho star is minimized. And why is this a good idea? Well, precisely because when you evaluate this objective, you actually don't need to have samples from rho star. So this pullback diver is actually an expectation of a rho theta, and this is something you know how to sample cheaply. So you can write a stochastic, a Monte Carlo approximation of this objective and run SGD on the parameters to adapt your model. And this is why I just call it variational inference on steroids, because instead of maybe just, optimizing the Bernoulli component of factorized distribution to describe the system, you're actually optimizing a bunch of deep neural networks to actually match your target distribution. So it's just a much more explicit ansatz, if you want, in this procedure. And indeed, if I just show you a simple example of a bimodal distribution that is the 2D mixture of Boltzmann with the marginals that are on the right and top axis. And if I show you what happens if I start from an initial rho theta that is like this, and that I run SGD on the objective I just wrote, well, and there's a neural net that is parameterizing this rho theta behind the scene. You see that you can indeed construct an approximation that looks like this rho star. It's not perfect by any means, but you've really narrowed down the high density regions with such a procedure. So the length is an artifact of the parameterization of rho theta. The way it's done, it's really hard to fully separate point masses, but down the line it would not matter so much because this is a negligible fraction of the mass. So, but okay, of course, you'll be convinced probably. Then, well, okay. However, so this objective is nice, but we know that it can be quite tricky. And in particular, if I run the same simulation, but now I start from initialization that is like this, then I will see something like this happening. So it's something that is actually has even a jargon in machine learning. It's called mode collapse. When you have a generative model that is going to focus only on a region of your space of interest, and in particular, here, so just collapse onto one of the two modes. And this is okay. This is something that I think is not well understood as it should be. And if you're interested, I'm happy to work in this direction. But there's non-convexity involved. But anyway, what happens is that you have this proneness to mode collapse. And here I could show you that with a good initialization that was well covering the space, you could get to a result of this. But in high dimension, it's actually hard to fight mode collapse with this objective function. So you need something else. Yes.
Do you think it might help to inject noise or something to maybe kind of get out of the region where it seems to be stuck?
So I don't know exactly how you would go in injecting noise.
Just in the optimization. Like, is it correct to say that it's maybe just stuck in a local minimum, or
it's stuck in a local minimum? That's correct. But I think there are effects also of the parametrization that makes with this objective, it's going to be, I mean, it's not that disadvantageous to be there instead of there. So I think it's very hard to, but I don't know. Yeah, we could chat about this. Okay, so.
Excuse me, does the
Yes.
relative weight of the two modes play a role here? I mean, in the sense that it collapsed not to something, it collapsed to the mode with the largest weight. Is that?
I'm not sure.
Okay.
I don't know. I think if I initialize through there, probably that just would be the closest.
Okay.
So, but I think it's not, I mean, of course, the actual geometry behind it has a lot of parameters and so on. So we don't know exactly. And that's actually even in simple models. So I think it's a nice problem. But anyway, so what we imagined instead was to resort to something that is adaptive MCMC. So an adaptive MCMC is a strategy in which you are going to simultaneously run a sampling algorithm and adapt your sampling kernel as you produce samples. And so here, what it's going to be provide for us is a way of approximating the maximum likelihood objective. So the maximum likelihood objective is the one I presented earlier, and it actually corresponds to minimizing the Kullback-Leibler divergence, but the symmetric version of the one I was just mentioning in the previous slide. And the way to do it schematically is the following. So I have the same toy target, and I start with using a local sampler, like the one I presented at the very beginning of the talk, so the Gaussian random walk or the Langevin algorithm, to produce some samples. So, of course, if I initialize a walker here and a walker here, and I let them run, then I'm going to produce samples like this with the statistics that are, on the two axes. So those samples are good, provide me with information of where are the regions of interest, but they don't provide me with information on what's the relative weights of the two different modes. But what I can do is use them to pre-train a model rho theta that would match the data sets that is formed by those first samples. And if I do it this way, I obtain a model like this that has captured where is the local geometry, let's say, of the region of interest, roughly, but that didn't have any information about the relative weights of the modes. But now what I can do is use this one as a proposal in a metropolis async MCMC. So here I have a distribution I know how to sample very efficiently that has a very good overlap with my target distribution. So if I run an MCMC where I propose with this one, independently of the previous step at each type, I will be able to have a mixing procedure in between the two. So here is just an animation of one such LCMC chains, where in the end, you have really a worker that is going to visit the two nodes, and it's reweighted with respect to the blue targets. And so it's going to start seeing what's the actual difference of weights of the two nodes. And here I decompose doing these steps, but actually what we do is all together. So you run 2 steps of local, 2 steps of training, 2 steps of global. And we do this until convergence. And if you want, the simulation looks more something like this, where you initialize your sampler in regions of interest. We have no way of discovering them in this algorithm. And then you have everybody, and you let everybody, all these processes of both MCMC sampling and training on the MCMC samples converge.
If you MCMC will not satisfy the data value.
Yes, so the at what it does at each step where you stop training, right? I mean, if you look at the full procedure where the kernel is changing, it does not. So there are ways of showing that the such adaptive MCMC converge to sampling from the target. Yes, you can, but I mean, what is unsatisfactory about these proofs, which I'm not going to mention, but we could, is that you need to assume that your initial proposition kernel is uniformly, the ratio between this density and the density of your target is uniformly bounded, which is which is not exactly what we need, but that's what the proof needs. Yes.
So key data here, does it have a specific form, like a Gaussian or something like this? Or?
It's a generative model. It's the if you want the Gaussian composed with the map. So it's the push forward of the Gaussian through the map, I should say. And this map has millions of parameters.
So you can potentially create a multimodal distribution.
Yes, well, it can. So
multimodal, so you will want that data can create a multimodal.
Yes, so I mean, it will most easily create things like this. So it's still connected.
So
but it doesn't matter.
One that is jumping back and forth between the two, so like or it could actually really create nodes. I don't know if you know what I mean.
So it, I mean, it can, but at the price of the training that you don't want to. I mean, and a price of the Lipschitz constant of the map. I mean, if you're thinking of the 1D problem, if you want, it needs to be extremely steep at some places, and if you look at the inverse, extremely flat. And then computing inverses is going to start to be touchy. So, so in the end, you have this, but you don't really care, because if I look at the statistics of the samples I'm producing with an MCMC that uses this as a proposal, nothing in this thread is never going to be accepted. And few things in this thread are going to be proposed because there's actually not so much mass. And this is where I started to already answer the second question of, okay, and this is just maybe for the sake of time, just going to pass the slide on the algorithm, but it's just writing down the lines of this metropolis hastings combined with maximum likelihood grading steps and doing everything at once. But precise, and here I was like, I'm finished with the how can we train the flow to approximate the targets. And I started already to answer about how to use an approximate model to sample reliably the targets. And this is, for example, using it as a proposal in the metropolis hastings, where just the accept reject criteria is going to debias your estimation by the flow, if you want. But you could imagine other ways. So this is the one we already discussed. But for example, if you're familiar with important sampling, this is a very natural algorithm to use in this case. So say you have this approximation, then what you can do is draw a bunch of samples from this approximation. So you can see that there would still be some in the middle, but then we weight them using the importance weights, which are just the ratio between the target density and the proposal density that you then insert inside any empirical expectation you're trying to compute. And here what I did is that I changed the radius of the points compared to their weights. And so you could see that compared to the original draw, you don't see anymore all the samples that are completely out of the support of the target distribution. And so I mean, it gives you an idea that actually you can reweight samples if you have a good enough overlap between your proposal and your targets to estimate expectations. So, okay, so I'm sure I'm doing really badly on time.
Well, 5 minutes.
5 minutes, okay. So if you want, I insert this conceptually those two questions of how can we train and how can we debias what we have trained, if you want, and have reliable sampling procedure. I mean, all of these are I mean, to an extent, rather simple ideas, but they are using down the, behind the scene, those very complex learnable maps that I completely put under the rug today. But then, I mean, now what we are trying to do is to explore really what are application cases in which this technology could be useful. So something I already mentioned is this question of Bayesian inference. And I have a former colleague and collaborator, so Kate Wong, who works on gravitational wave and so the analysis of the data of gravitational waves. And for example, it claims that if we have fast inference algorithms, then we could be able to, if you want, point at events in the sky because we locate them fast enough before they are over. So if you want to infer the position of the events in real time as you receive the data in order to be able to point more measuring instruments at it. That's one case.
Sorry, and then can you go back to the so you're basically doing distance based estimation, right? I mean,
What did you say?
distance based estimation. So using the scale distance, using distance based estimation.
Yeah.
Between two things, one of which you vary from the other is big. Why do the scale? Is it just for computational convenience so that the law helps you out with the audience or your flows? Or is there, could you use other distances, or is it inherently limited to the scale?
No, I don't think it's inherently limited to the KL. So here, I think there are most often time computational hurdles that doing something else than, for example, this maximum likelihood, which you know is pretty robust. And here you have all the ingredients to do it. But I mean, I'm happy to discuss using something else.
Sorry.
No, thank you. Yes, so that's one example of application, and actually, Chris has been very motivated in driving this effort into making this out of this package out of the concept. And maybe I should have also credited more explicitly Yvonne Allen and Brett Rostock with whom. So we worked on this paper with the adaptive LTNC. So now, yes, on the application side, Kate has been leading this effort to make a package that is fitting syllable. So I mean, your curiosity has been aroused by the talk. Feel free to have a look and provide us with any feedback or any idea of what could be good case studies for this kind of algorithms. But okay, before I wrap up, I really need to tell you about what are the main limitations of this approach. And here again, I mean, no free lunch, we are faced with the curse of dimensionality. So here, it's actually a test that has been done by, in this PRD paper of Gabrié and collaborators on a statistical mechanics model. So some of you might be familiar with this 5-4 model, which has a phase transition. So it's a model on a grid of scalar value field, so 2D grids. And as you change the temperature, you are going to have a different behavior of the model. You will have a ferromagnetic space where all the values of the grid are more or less equal. And here you have whole white, that means all 1. And then you have a critical temperature at which things are actually self-center, and you have black for -1 and white for 1. And you have a disordered phase at higher temperature. And so they try to sample configurations of this type of system, varying the temperature and varying the size of the problem. And they trained a new neural net to produce each of the points in this diagram. And they tried their best to, if you want to make the best neural nets to best approximate each of size and temperature configuration of this physical system. And what they recorded is the acceptance they get in the Metropolis Hastings after training, when they are trying to just propagate in a sense chain. And what you can see is that at small models with like 6 by 6 grid, you have almost 90% of acceptance. Everything going fine, you're MCMT converting super fast. But as you are increasing the size of the model, and they go up to 2550, so darker colors, you can see that the acceptance is systematic, and in particular, so at the critical temperature. So there is this idea that, well, indeed, the more complicated gets the task, be it because it's higher dimensional, or be it because we believe the geometry is harder and harder at the critical temperature, then the lower will be your acceptance until, you know, if you really wanted to study a very large system to have really, you know, how should I say, phase transition-like critical behaviors, then you will be eventually hitting a 0 acceptance threshold, where it means that you've been working a lot, spending a lot of GPUs training neural networks, but actually there are no use for your inference. So this is right now the main limitations, and I will not have time, I guess, to give you all the story of how this can be tackled, and at least in which directions we are pushing. Some of them are trying to actually put as much physics as we can in the parameterizations of the models before leaving the rest. So everything we can handle analytically, if you want, before leaving the rest to the machine learning. There are also ideas of relying on more on gradient information and not doing only independent move in the server. But okay, this is I guess for another time. And with this, I would like to thank you very much for your attention. And I have a list of the different references that all of this is trying to summarize. But okay, I'm happy to chat.
So let's have a few questions. Yeah.
Short presentation. When you look at these models that, you know, always push forwards, like the stuff that you looked at, and then you compare to this continuous time models, you can also ask yourself, you know, what happens in your thing when you go to the continuous time limit.
Yes.
And sort of what puzzles me is sort of like this spot distribution models, you always have this drawing motion additionally injecting noise, which I think relates to answer question. So I don't know, do you ever discuss about the continuous time limit of things?
Yes, so this is now we are working more with continuous time limit. I mean, with those models that are parameterized in continuous time, and there are a few of them, not only the score-based diffusions actually. But in this case, those models, they are really just a way of implementing this map T theta. It's not. I mean, there is you learn. Well, no, it's true that you are still simulating an SDE, but you have an equivalent ODE to any SDE. And in the end, what your simulation is going to give you is the output of this equivalent ODE or the SDE, but what you care about is the distribution of what you get. And so
it's noise, and then you transform it away because of the random.
Yes.
Okay.
Well, yeah, I think here there is no direct way of I mean, you can use them exactly as I did, but I don't see any other way of exploiting what they are and the difference with the time with discrete maps. Yeah. Yes.
So how much computational cost do you have, like, using this new proposal?
It depends highly on your problem, right? So you should think of this as being useful if, so for example, you have multimodal distributions, you know where are the modes, but you don't have a fast algorithm, or maybe you don't have a good reaction coordinate to organize the transition, because of course there are plenty of algorithms you could use to make this transition. But here, I mean, you just know about your system and you don't know anything about the transition path or good reaction coordinates. Then you can train a generative models that will help you just jump from one basing to the next, not learning anything about the transition. But here I'm just giving you an argument for why it could be useful in general, because you don't know how to do it any other way, but it does have a computational cost.
You have a problem with BC. Let's say,
Yeah.
well, can I use some preconditioner to take this problem? Then, well, this approach we can use better proposal.
Yeah. So, but, okay, I mean, if you have ideas of application, I mean, I'm curious because in the end, yeah, then I think whether or not it's useful will be really problem depending.
Just maybe do the break and we take all the questions.
Yeah,
offline, I guess.
yeah.
Thank you.
Okay, thank you again, Marylou.
We have 15 minutes for the break.
Yeah, grab a coffee and have to eat and back in 15 minutes.